Hi, in this short video I'll present our work on sparsity-inducing optimal control via differential dynamic programming. To begin, consider a high-dimensional robot and a lower-dimensional task. Now the high-def robot, such as the Valkyrie, can reach in front of itself by moving the entire body and all the joints. That is arguably an unnecessary motion, as we can achieve the same result by moving the torso and the hands only. Next, consider a satellite planning problem. A satellite has a series of thrusters which due to hardware limitations are either always off or always on. I'll argue that these two problems are connected, and what they have in common, in fact, is sparsity. Sparsity for the high-dimensional robot, the Valkyrie, means that most joints are not moving or are at zero, also known as parsimonious control. Sparsity for the satellite problem means that most controls are zero, corresponding to the thrusters being off. Sparse models are used commonly in machine learning, where they are used for model selection. There, L2 and L1 costs are added to the model to the cost function, where L2 is used to penalize large weights, and L1 specifically is used to induce sparsity. Here we show what L1 and L2 look like. L1 is defined as the absolute value of its argument, whereas L2 is the square of its argument. The gradients for L1 and L2 are different though. The gradients for L1 is constant, which means that it'll readily drive its argument to zero, whereas the gradient for L2 becomes smaller and smaller because it's a function of x. So near zero, the gradient will be very small and the weights will never actually reach numerical zero. In this paper, we consider sparsity for motion planning specifically. So here I've shown a corpo, a dynamic system, and the controls, the input forces over time. The L2 trajectory is the smooth trajectory in blue, and the orange trajectory is the sparse trajectory. So we would like to have motions that are sparse, like the one in orange here. In this paper, we consider optimal control, which is a way of solving a motion planning problem, or planning a motion. A motion is a collection of states, positions and velocities, x, and controls, or forces, u. For the corpo here on the left, the controls or forces applied to the cart. On the right, we formulate the simple optimal control problem. We optimize a motion planning cost, j, subject to constraints. The first, that we obey physics, that we start at a known state. For the corpo, this is with the pole pointing down, and end at a goal state, and for the corpo, this is with the pole pointing up. Traditionally, motion planning costs are L2 regularization on control inputs. This is done over all controls summed over the entire horizon, with a weight lambda applied. Here we give two examples of papers using L2 regularization from the quadruped domain. In this paper, our scope is differential dynamic programming, which is a method for solving optimal control problems. DDP is a shooting method and optimizes over control trajectories only, and it breaks down the problem in time and recursively solves smaller subproblems, and as such it's faster. We use specifically a direct-indirect hybridization approach as referenced here. DDP itself describes the problem and the regularization in one cost function. So it encodes the task in H here and the regularization in LS. In this paper, we propose using the L1 regularization instead of L2, specifically replacing the cost function LS by an L1. Here we show a trajectory on the corpo with an L1 regularization, where we see control peaks at the limits or below the limits in red. We see sparsity as well, with most of the controls being zero. We cannot, however, use an L1 cost directly in a gradient-based optimization, such as DDP, as it has an undefined gradient at zero. However, approximations exist from the machine learning community, and in this paper we studied 3 of them, and they all share the same idea, which is to replace an L1 cost with an L1 cost for large x only, but for small x with the threshold beta, use an L2 loss, which has a gradient around 0. This introduces an extra parameter. So currently we have a control weight parameter, shown on the left here, in the DDP cost, and we have introduced the switch parameter between L1 and L2. We would like to measure the effect of those parameters on 2 metrics, namely the numbers of zeros, whereas a control is considered 0 if it's within the range minus beta to beta, where the switch is, and the final task cost h, which tells us how well we've solved the motion planning problem. Here we plot the number of zeros and final task cost on the corpo example. As we see, increasing lambda leads to more sparsity, which is expected. However, it also leads to a lower task cost, which is also expected as lambda is the mixing parameter. We also notice that for smaller beta, we need bigger values of lambda to achieve a similar level of sparsity. Since the larger weight, however, leads to more aggressive controls, we see control artifacts on the right. With that in mind, we propose the following tuning scheme. Pick the switching parameter beta, depending on how much noise the system can tolerate. This will come from hardware limitations or design requirements. And then tune lambda depending on the desired degree of sparsity and desired final task cost. Here we show the result of a tune optimization on the satellite task. We track a center of mass trajectory, however we plan with full rigid body dynamics and sparse L1 penalties and controls, and we can see that we achieve the desired thruster profile with peaks when the thrusters are active and zeros where they're off. Now we have two types of thrusters with two different control limits, and we can see the corresponding peaks of those control limits. Compared to previous approaches, we use the full rigid body dynamics of the satellite and do not model the thruster separately, but rather use a penalty cost to achieve the desired profile. Even though we track a trajectory, a center of mass trajectory, we plan for the full body dynamics of the satellite with a full dynamics model. Next, we use an L1 cost to achieve active joint selection for the reaching task. An L1 cost will automatically select the required number of joints by virtue of setting the others to 0, and in this case we can see that 3 joints are active, but because of noise we actually have 7 joints active on the robot. Nonetheless, we see that motion in the legs is significantly reduced, and in fact the torso is used to move the robot to the right position. Compared to previous approaches, we used differential dynamic programming and not a constrained QP solver such as in 1, and we introduced sparse cost to the DDP's cost without using constraints, as well as using a kinodynamic model versus a purely kinematic model in an IK approach. A benefit of sparsity is that we can achieve better tracking on the physical robot. Since fewer joints are moving, we see better tracking during the trajectory and after the end of the trajectory for the Valkyrie reaching task. A drawback of L1 is the increase in computational time since we've made the problem harder. For all variants of L1, we see an increase in computational time. Here we plot the time for the satellite example for different regularization strengths, lambda. Here we show a video of the satellite trajectory showing the thrusters firing at the start and end stages of the multi-stage center of mass trajectory. And here we show the experiments on the Valkyrie robot. The L2 loss uses all joints and balances the weight of the robot on one leg, whereas the L1 loss moves the torso. We also show another satellite tracking trajectory with a different center of mass reference trajectory. In conclusion, we introduced L1 regularization to a family of DDP-derived optimal control solvers. We studied their convergence properties and the effect of the free parameters. We applied sparse cost to a satellite problem, showing that we can plan for thruster-like behavior with a control cost penalty. We used full dynamics for the satellite and tracked the center of mass trajectory. We also used sparse costs to actively select the required number of joints for a lower dimensional reaching task. Future work can add to the full satellite dynamics model, potentially adding a payload. And also use the full rigid body dynamics for the humanoid robot, thus exploiting the natural dynamics of the system. Thank you.